Welcome. This video is from Section 3, Chapter 5 of the Brown IB Chemistry book. And in Section 3, we look at something called bond enthalpies, which basically are the opposite of heats of formation. So you can make new compounds by forming bonds, and then you can break those bonds apart. So the bond enthalpy is the energy needed to break 1 mole of bonds in gaseous molecules under standard conditions. So not standard state, but standard conditions. So when more than one bond is present in a molecule, like H2O, even though the two hydrogen-oxygen single bonds are identical, the first bond always requires more energy to break. And then once you've broken that first bond off, now your remaining molecule is unstable, and it's going to be easier to break that second one off. And also, another thing to keep in mind is that the hydrogen-oxygen single bond in another substance like ethanol or any alcohol is going to be different than it is for the bonds in water. So bond enthalpies are given as an average, and the symbol for bond enthalpy is capital E. And so single, double, and triple bonds between the same atoms, like an oxygen-oxygen single bond, an oxygen-oxygen double bond, those also require different energy. So when you're looking up the value on a chart, you have to make sure you're looking for the correct atoms and whether it's a single, double, or triple bond. So, for example, the energy change when two chlorine atoms form from a chlorine molecule is shown here. And you notice that the states are given. They're both gases, all substances, both of them. And they don't contain any bonds. And another thing to notice with bond enthalpies is now it's a positive sign. Because remember, when we had bond formation, that was exothermic. So those values are all given as negative values. But bond enthalpies are going to require energy. So those are going to be endothermic processes and going to be positive values, and again given in kilojoules per mole, just like the bond formation was. So the bond enthalpy for chlorine is given here, and if you look at the two below, I also included these two. I notice I got cut off a little bit, but we can work with this. So the bond enthalpy for the OH bond in water can be represented as H2O gas being split into H atoms and O atoms, and actually I need a 2 here. I don't know who my source was for this, but I need to have 2 H atoms and 1 O atom. And then down below, it can't be expressed as H2O gas being formed as an H2 molecule and half an O2 molecule, because now there's bonds in here that we have to consider. Even with half an O2 molecule, there's a bond that's associated with that. So you have to split it into the constituent elements. They all have to be gases in order for it to be considered a proper equation, a proper measure of bond enthalpy. So energy is always needed to separate the atoms because of the attraction between the nuclei and bonding electrons. So bond breaking is always going to be endothermic. So again, the bond enthalpy values are given as positive values since it's endothermic. And it's always compared in the gaseous state. And the reason why is so you don't have any intermolecular forces interfering and increasing the energy needed. If you're interested in just the bond energy, that would be most easily measured, most accurately measured in a gaseous state. And then again, the bond enthalpy should be the same amount of energy that was released when the bond was formed. So just kind of some reminder notes or summary of what bond enthalpy is all about. And let's start looking at how to use this. So endothermic processes involve the separation of particles. You're putting energy in, so you're moving particles further apart, whereas exothermic processes involve bringing particles together, which have an attractive force between them. So I want you to label each of the following as an endothermic or exothermic process. And so I would encourage you to just pause and give this a try here. And I'm going to pause and label it myself. So as I look at these 2Cl to Cl2, I'm bringing particles together. So this is actually an exothermic process. And my second one, Na gas becoming Na plus E minus, that involves separating things. So that's going to require energy. That's going to be endothermic. Bringing two ions together, it's just that you're bringing them together, so that's going to be exothermic. and a gas to a solid, it's also going to be bringing them together, so that's going to be exothermic. So the only endothermic process here is the second one, when you're removing an electron, ionization. To form products in a reaction, new bonds have to form. So again, bond making is always exothermic, and that's why heats of formation are negative values. And if the new bonds are stronger, if they release more energy than the bond breaking absorbed, then the reaction is going to be exothermic. And that will also be expressed as a negative enthalpy change, since the heat's going to be lost to the surroundings. And then conversely, if new bonds are weaker, the reaction is considered endothermic, and this means we can calculate the change in enthalpy for any reaction using bond enthalpies. So this has given us one more variation on Hess's law. We can sum up the steps, we can look at heats of formation, and we can also look at bond enthalpy. So let's look at an example of how you actually use bond enthalpies to calculate the change of enthalpy. It says to calculate the energy change in a reaction, you need to know all the bonds to be broken as well as the bonds to be formed. And so now you're going to take your bonds broken minus your bonds formed. And remember, your bonds broken are in your reactants, and your bonds formed are in your products. And this should make sense because we're using the values opposite of the heat of formation, so we just flip the equation over also. So my problem here says use bond enthalpies to calculate the change in enthalpy for 2H2 plus O2 equals 2H2O. Now, if you want to express this as kilojoules per mole, which it often is, this equation could also be rewritten as just H2 plus half an O2 gives you H2O. And then, of course, you'd have your state symbols, all as gases. Either one is fine. If I go with my original here, I'm going to have H2 is just a single bonded hydrogen, oxygen double bonds to itself, and water has two single bonds in it. So the way the equation's written, the top one here, I need to find the value for a hydrogen single bond and multiply by 2, add an oxygen double bond to that, and then subtract. I actually have 4 OH bonds that I have to subtract from that. So this should yield the change in enthalpy for the formation of water. So if I find a chart, and I'm going to use the chart on page 186, it gives the value for the hydrogen single bond as 436. And values are going to vary a little bit on charts. It depends on which bonds they averaged for this. So don't be shocked that you'll see slightly different values, different experimental conditions, etc. And then my O2, my double bond, is 498. And then I need to subtract 4 times the OH, which is given as 463. So when I do that, the value I'm going to get, the value I get is a negative 482. So up here I'd write as negative 482, and I would just label this kilojoules because this isn't per mole. If I were doing it for the second equation, then I would divide this by 2, and this would be negative 241 kilojoules per mole. And either way is fine. You just have to be aware of when you're labeling if it's appropriate to label it as kilojoules per mole or not. So here's one for you to try. It says use bond enthalpies to calculate the change in enthalpy for the combustion of methane. I've given you the formula for methane. And remember, combustion is going to involve oxygen and will yield CO2 and water. So go ahead and pause and see what you can do on this. And then watch my solution. So I'm going to have CH4 plus O2 is going to yield CO2 and H2O. And these are all in the gaseous state. I'm not going to bother putting the symbols in as a practice, but this means I have 4 CH bonds here. O2, I have just the one double bond. Oh, I should go back and balance this first, though. So I need a 2 here for the 4 hydrogen. And I've got 2, 3, 4, so a 2 here. So that lets me know I'm going to have 2 of the OH bonds, and then I'm going to be subtracting the CO2 has 2 carbon-oxygen double bonds, and the water again has an OH bond, 2 of them, and I've got 4 water, so I'm going to subtract that. So now when I plug values in, CH is 414 times 4 plus the 2 oxygen bonds, 2 times 498, and then the 2 CHO bonds are, because they're double bonds, they're 804. Plus the 4 OH bonds are 463 each. So what I've done is I've added up the reactants and products each separately, and you can see that the reactants are going to require 2,652 kilojoules, and the products were requiring 3,460. So then my difference is negative 808, and this would be kilojoules per mole. Here's another one I wanted you to try. Calculate the change in enthalpy for the following reaction. And here you have C2H4, and it's going to undergo what we call an addition reaction. It's going to be saturated with some hydrogen to form C2H6. So go ahead and try this yourself, and then I'm going to walk through my solution. So C2H4, it has a double bond. That's why there's only 4 hydrogens attached. And then the H2. And then the C2H6 is what we say is saturated because it's got 6 hydrogens. It's got the maximum number of hydrogens that it can hold. So I've got 6 CH bonds over here plus the carbon-carbon single bond. So here's one thing you could do is, just like in any mathematic problem, because I have 4 CH bonds here and 6 CH bonds here, I don't need to put a value in for these. I can actually just cancel it here. I know I've taken 4 minus 6, so it's really a net 6 CH bonds. So that's what I'm going to do. So when I plug in, my carbon-carbon double bond has a value of 614, and then the hydrogen bond is 436 minus just the 2 CH bonds net that remain or get added, plus the carbon-carbon single bond now is only 347. And now I can go ahead and do my plug and chug, and I get a negative 125 kilojoules per mole. So to sum up the 3 different methods we have the original with Hess's law where you sum up steps. So that's easy to know if you should use Hess's law because they're going to have to give you the equations. You're not expected to go find those. But the standard heats of formation and bond enthalpies, those are a little trickier because you can look up either. So it depends on what information you have available. But again, the book usually tips you off. Most problems will tell you use the heats of formation or use the bond enthalpies to calculate this. So with heats of formation, you need to sum the heats of formation for each reactant and each product. So that's just one value for each reactant and product. And then you take products minus reactants. And then with bond enthalpies, you need to sum the bond enthalpies for all the bonds found in the reactants and products, although you can simplify that if you have the same bonds occurring in reactants and products. And now you find the difference from reactants minus products. So how do you remember if you take product minus reactant or reactant minus product? What I remember is that bond formation is exothermic, so values when you're forming bonds is going to be negative. And bond enthalpy is endothermic, so values are going to be positive. So if I'm using heats of formation values, heats of formation values are always given as negative values because it's an exothermic process. So when I think about it, if I have an exothermic reaction overall, my product should have should give off more energy than my reactants. So when I take my product minus reactant or my reactant minus product, I should get a negative value. And the only way that's going to happen is if I take a negative product minus a negative reactant, I will end up with a negative value overall for an exothermic. And then for enthalpy, bond enthalpy is a positive value. So if I'm taking positive values of products minus reactant, and if I want a negative value for an exothermic reaction overall, now I'm going to have to take my positive reactant minus my positive product to end up with a negative value overall if it were an exothermic reaction. I hope that makes some sense, but that's how I reason my way through it. Is I look at the fact that heats of formation are negative values, enthalpy are always positive values, and what would have to happen to yield an overall negative or positive reaction? Which way would I subtract?